Swayam Prabha. Digital India. Educated India.
In this third lecture of module 5, we continue to discuss the surface reactions. Today we look into catalytic effects, reactions in emulsions and complex formation in monolayers. We had seen for alkaline hydrolysis of octadecyl acetate, long chain quaternary compounds like amines could facilitate attraction for negatively charged hydrolytic hydroxyl ions and thereby accelerate the reaction, and addition of a neutral salt could modify that behavior. For instance, if we had only octadecyl acetate alone, the rate constant would be about 0.93 into 10 raised to minus 2 minutes inverse, whereas if you have a concentration of about 12.5% of the long chain quaternary amine compound, the rate constant would jump to 7.4 into 10 raised to minus 2 minute inverse. And if we increase that amine concentration to about 33%, then the rate constant would rise to about 15 into 10 raised to minus 2 minutes inverse. What it means is that we achieve here acceleration of reaction by the quaternary ions by a factor as high as 16 to 17 times. That is a significant increase in the reaction rate. An order of magnitude increase will always be desirable. One could rationalize these effects of charge on film through the equations by identifying the surface potential psi by the Goe potential, for which we know the expressions. That is a generic expression, and the corresponding expressions at 20 and 25 degrees centigrade are the ones which you already know. As you recall, the Goe equations are based on a model where there is a uniformly charged plane and the counter ions are all represented as point charges. Alternatively, we could take Donan treatment, wherein not just the monolayer, which may be insoluble, but an immediate layer of subjacent solution would be regarded as the surface phase, and that would be of non-zero thickness. And within this finite region, the counter ions are all presumed to be concentrated, and with that presumption, the effect of neutral salt concentration on the rate constant is the one corresponding to the curvilinear line shown in that diagram. Now, one may discuss this a little further, and catalysis by an electrical charge has found applications in degradation of large molecules, as shown in the work of Steinhardt and Fugit in 1942. We could achieve hydrolysis of protein by a factor of 100 or more by using lauryl sulfonic acid in comparison to HCl. Now, this is something I would like you to think for a minute. Think of protein being hydrolyzed, and you take a weak looking acid, lauryl sulfonic acid. Contrast it against the acid hydrolysis you may achieve with the strong hydrochloric acid solution, and you find this unusual, unexpected result. The hydrolysis of proteins is a lot quicker, 100 times, 2 orders of magnitude quicker than with HCl. How would this possibly explained? Any ideas? Please remember the basic tenets are very few. I mean, most of what we will retain as take home message from the lectures on reactions, apart from the details of reaction, are very few. So, and I would like you to connect with that understanding of generic features at every stage. It looks counterintuitive, right? Lauryl sulfonic acid achieving 100 times quicker hydrolysis of protein than HCl. The example we just discussed, the quaternary long chain quaternary ions adsorbed in the monolayer attracting hydroxyl ions, may serve as a hint. If you want to build on that hint, how could we explain the protein hydrolysis?
So in case of HCl, it won't get absorbed, but in case of lauryl acid, the part which is hydrophobic will get absorbed on that particular. So there is more interactions.
It's a part of the explanation. What will be the effect of that adsorption? That's the question we should ask. One thing is clear, this is acid hydrolysis. Protein is attacked by acid and it is hydrolyzed. The strong HCl is unable to do it as quickly as this lauryl sulfonic acid. So, the complete explanation will be following, that on top of protein, these lauryl sulfate ions will get adsorbed and attract hydrogen ions to that region, thereby achieving a lot higher concentration of H plus in the vicinity of protein. Acid is H plus is what is responsible for hydrolysis, whereas in case of HCl there is no adsorption driven concentration of H plus ions near the protein, so that will not be able to break it down, right. So, the principle is very simple. In a surface reaction, we are achieving a very high concentration of the reactive species. In the monolayers, it will be a location in the surface phase. In case of proteins, it would be at the surface of proteins. And we will build up this understanding a little further with other examples. But let us note in passing that when you compare peptide linkages, peptide bonds with amide groups are CONH2 groups. The peptide bonds are CONH CHR. We find that these amine groups are preferentially broken, whereas the peptide bonds are more resistant. Selective catalysis of this kind, possible in surface reactions, can therefore be an important tool in investigating other large molecules, how they react. And these large molecules could be in one of these forms. They could be in solution if the material is soluble, or else it could be spread in surfaces such as of foams or emulsions. Examples would be terylene, nylon or polyamino acids. They are insoluble, but they could be spread at the interface and then the reaction could occur. With this, we move on to discuss reactions in emulsions. I broached the topic of reactions in emulsions in the very first lecture. We recapitulate that emulsions of oil and water can provide very large areas. Because that large interfacial area is there, we might be able to achieve reactions which require surface. They could be of two kinds: reactions like saponification or emulsion polymerization. So, let us look into the reactions in emulsions in these two categories as we go along. First, we think about emulsion polymerization. It would require an intimate contact between the monomer surface and a water soluble catalyst, and the reaction rate can be affected greatly because we may now be able to achieve a high reaction rate even at room temperature. What is an immediate advantage of having a practicable rate of reaction at room temperature? First and foremost is that we will be able to avoid the undesirable product formation. Generally, these are branch chain compounds which are not desirable but get produced at high temperature. By achieving feasible reactions at room temperature, making use of high interfacial area and energy of the interface, we might be able to overcome that first undesirable part. The second part is, of course, if you can carry out a reaction at room temperature, it is an energy saving. So, that means the cost of your process could be brought down. Could there be a potential application in block polymerization? You could think of an example like this. Supposing that you want to produce a block copolymer of species A, monomer A, and species B or the monomer B, such that monomer A may be water soluble and monomer B may be oil soluble. So, you basically looking at making a copolymer of A and B with certain repetition of the monomers of A and monomers of B. One could get this started conveniently in an emulsion as shown by Dunn and Melville in 1952. He started with a monomer A which is water soluble, and the polymer radicals which are generated in this phase will first create short chains like the one indicated here, a few A's, and when these come in contact with the water insoluble monomer B, they would add a B unit. An example of this is acrylic acid could be dissolved in water. It would form oligomer molecule species in water and then add the other species like styrene from the oil phase. You would need obviously to catalyze the reaction of acrylic acid molecules a photosensitizer like uranyl nitrate. So, you could get a copolymer of acrylic acid and styrene in emulsions this way. The fats may be hydrolyzed also in emulsions. You all know how soaps are produced. You react a vegetable oil with alkali at a high temperature, and that would result in formation of soap. The speed of saponification or the total soap formation rate in terms of amount per time will obviously depend on the fineness of emulsion or the total interfacial area available in your system. Finer the emulsion, better will be this fat hydrolysis. You could think of another example of emulsion polymerization, that of styrene. Here there is a slight difference. In case of emulsion polymerization of styrene, the polymerization does not occur in or on emulsion droplets. Rather, we have to look at this situation. Could we have the visualizer, please? So, we first look at this. Let us say we have air and water, and we are thinking of now adding surfactant, long chain, hydrophobic, and the hydrophilic head group. If you keep adding such amphiphilic molecules, you would find that first these all get adsorbed at the surface. When this surface is completely occupied under given conditions, any additional amount will require these surface active molecules to occupy position inside bulk of water, and you know that energetically that is not favorable. So, one may expect that probably there may be some further adsorption at the surface, but that cannot be indefinite. Once the capacity of the interface to pick up or contain these molecules is exceeded, then these added molecules will have no option but to be inside the bulk. But we know energetically this is not favorable, because this is disrupting the hydrogen bonded structure of water. So, what these molecules do is the following: hydrophilic head groups are fine, water can take them, but hydrophobic tails are not preferred. So, there is a self assembly now, wherein all these additional amphiphilic molecules rearrange themselves in a shape like this. This is a 2-dimensional picture, just a cross section of a self assembled structure made by molecules of surface active agent. Actually, it will be a spherical 3-dimensional structure, and that is what is my cell. So, lots of these micelles will form depending on the properties and concentrations, temperature. We may get different geometries. These may be spherical, or they may be cylindrical, lamellar, many other geometries are possible. But the important point to understand is, now these head groups make those additional molecules which were not favorable energetically to be reassembled in an acceptable manner, because spheres of hydrophilic external surface will be completely acceptable by water. The tails are in vicinity of each other, hiding away from water. So, this is an intelligent arrangement that the molecules are realizing, making micelles. Now, if that is the case, then apart from this hydrophilic exterior surface, we see that in the bulk of this we have hydrophobic environment. These are all tails, right. So, within the bulk of water we have these micelles with hydrophilic external surface and hydrophobic bulk. If you incorporate now other species like styrene, being hydrophobic species will be not acceptable in water, but it will be acceptable in the bulk of micelles. So, we might be able to get the styrene molecules here, which will make these micelles swell. So, we will have the swollen micelles with the interior hydrophobic region now solubilizing styrene. So, that kind of situation would arise in the emulsion polymerization, where now the polymerization will have to be initiated in the micelles of the surfactant or soap molecules. So, that is a different kind of surface reaction we have. What advantage could we possibly have in such a different kind of system? Think of one. Could there possibly be an advantage in achieving reaction in the core of a micelle? What would that be?
It will be for a closed molecular residues. The range will be short.
Shorter. That is, hopefully the micelles are all of comparable size, and because their size will be more or less similar, the inner core, hydrophobic core, will have similar volume and a capacity to take up styrene or similar species and achieve the reaction. So, you would be hopefully limiting the maximum polymer molecule size to the dimension of the interior of a micelle, and that thereby you will be able to have a more uniform molecular weight distribution. What else apart from that? Suppose I coin a different situation. Maybe I tailor make micelles in a different manner so that the interior is hydrophilic. Then I may be able to carry out a reaction like precipitation, and I may be able to create particles, maybe even micro or nano dimension particles. Either those particles or the polymer particles you are producing, what advantage you would have apart from narrow size distribution? The obvious one, the distribution has these two characteristics: how much is the spread and what is the absolute size. Because the micelles are going to be molecular level assemblies, the particles are going to be very small, right? Each micelle is like a reactor. The dimensions of that reactor will limit the maximum size of the particles produced. So, because these dimensions are very small, the particle sizes produced are also very small, right? So, there could be some advantages of carrying out reactions in this fashion. Some of the methods of making nanoparticles, producing nanoparticles, are based on micellar reactions. There could be limitations on amount of particles you can make depending on the micellar concentration. And again, to talk in general about interfacial engineering and our technological evolution. With the mind and technology, rate of evolution has jumped a million-fold or more, and although we have realized the significance of surfaces and interfaces for a very long time, the detailed scrutiny at atomic scale has been difficult, not just because the interfaces are very small regions close to the surface, but also because the properties are very drastically different from bulk materials. But now there are techniques, increasingly sophisticated techniques, which can give more insight into the composition and surface of a wide variety of these surface or interface systems. And as we become better in the characterization and manipulation of the surfaces, we should be able to create new applications, perhaps learn more about this fascinating new science. Returning to the surface reactions, I take another example. I had talked about making fibers. There is one example in natural systems which I had given, but you could think of another laboratory example here involving interfacial polymerization. You require a simple experiment in which you take two solutions, one of 1.5 cc of sebacoyl chloride in 50 cc of perchloroethylene, and the other solution is in 50 cc of water 4 grams of sodium carbonate and 2.2 grams of hexamethylene diamine. Looking at the molecules I am talking of, you would already have an idea. If I add this second solution of carbonate and hexamethylene diamine in water on top of this sebacoyl chloride in perchloroethylene very carefully, so that there is no mixing and the interface is planar, you would see the interface becomes milky white. A film forms which is a milky white film, and if you can carefully catch that film with a pair of tongs and pull it out, you would be able to continuously pulling out a nylon rope, very thin one. Now, obviously, this kind of experiment can be fully automated and could be used for producing fibers, very thin fibers of other polymers also, like polyesters or polyurethanes. We then take up a topic of complex formation in monolayers. Now, this is a different scenario. We are talking now about very small concentrations of heavy metal ions present in water, and the modification of monolayer of stearic acid present at the surface of such water. The monolayer of stearic acid, when contacted with this very small level of impurities of heavy metals will eventually create a difference. The heavy metal ions could be brought to the monolayer through the usual processes of diffusion and convection. We are not going to discuss mass transfer yet, but then what differences can be created by presence of these heavy metal ions at such low concentrations for the monolayer. Look at the numbers here, 1 part in 2 billion parts of water, 1 part in 2 billion parts of water, or 0.5 ppb of aluminum 3 plus is sufficient to alter physical properties of stearic acid monolayer. So, one could think of this effect to be made use of in, let us say, sensing the metal impurities. You might be able to use monolayers as sensors for ultra low concentrations of metals. In similar fashion, copper ions are also very effective in forming salts of stearic acid. Once again, the properties will be very different. Now, such studies which not only display or demonstrate the effect of very small quantities of impurities could also help us understand better the sensitization of monolayer reactions. And for example, a course of a photochemical reaction could be completely altered by the presence of heavy metal ions. We take an example for decomposition to proceed in films of alpha hydroxystearic acid on 0.01 normal HCl under the action of radiation of 2537 angstroms, subanalytical quantities of nickel ions must be present. The mechanism involves one molecule of alpha hydroxystearic acid combining with one nickel ion before CO2 can be split off. But if you do not have nickel ions, then alpha hydroxystearic acid cannot be decomposed. Or one could think of interaction of monolayers of fatty acids and long chain sulfates with ions of heavy metals which are injected below them. We would expect this interaction to be very much affected by pH. If pH is such that basic metal ions are formed in the solution, such as for example for calcium a complex formation takes place, but for basic ions no such complex is formed because of steric hindrance. Or you could think of adsorption of long chain ionic compounds from solution on surfaces of solid metals or their minerals. This could take place under certain pH conditions and stereochemistry. This would be similar to the conditions required by monolayer interactions, which means the monolayers can be a model or guide to investigate the possibility of flotation as a means of removal of particular mineral with the long chain compounds under consideration. So, one may not require to actually do the much larger scale flotation experiments, but insights into how that flotation, plant flotation may work may be guided by the experiments under a minuscule scale at the level of monolayers. That brings us to the last topic that we will get started with today, but not finish. If under a monolayer another species is injected, then what may happen? You have monolayer and you are injecting under the monolayer another molecular species. The simplest interaction between the two types of molecules will be mainly electrostatic. It will mean that this will lead to changes in surface potential with very small alterations in surface pressure. We could think of injecting very dilute solutions of long chain salts under many monolayers. To get an idea, we could look at this diagram. You have the monolayer first over here, and the added molecules are anchored into the monolayer, but it is just below this. This will be one situation. Another situation could be the added molecules could actually go on to penetrate the monolayer, and these are the species then finally making their way into a film. So, these are two possibilities. The added molecules may be anchored or they might be able to penetrate into a film. Yeah.
How is this achieved? As in, first there's water and with monolayer.
Right.
Then how do we inject such a thing?
Oh, we could do that with a micro syringe. You just take this other species, the ions from the other solution, and then you inject it below the monolayer. Once it goes under the monolayer, it will be brought to the surface by whatever convection there might be. If there is no convection, diffusion will bring it. Eventually, these other molecules will come in the vicinity of the monolayer. They could be anchored here, or they might be able to make their way into the monolayer. Now, if the energy of desorption is not very high, especially for the diagram shown over here, under compression you might be able to eject these anchored molecules. It might happen even here. It depends on the interaction among the molecules of two kinds. So, if one is adsorbed in much stronger manner at the interface, increase in surface pressure could lead to the desorption of the other species. Now, the penetration, if it is achieved in the monolayer, it is characterized by large changes in both surface pressure as well as surface potential. And the second aspect is not surprising, because we did think of surface potentials as an effective way of monitoring surface reactions. With some molecular species, contribution of each to the surface pressure and potential are independent. That is, the two species are contributing independent of each other to the surface pressure and surface potential, in which case we may regard the resulting film of two species as a simple mixture of two components, right. So, this kind of behavior is shown by astaxanthin and oleic acid spread on 0.01 normal HCl. At low pressures, we have the film behaving as simple mixture of two components. But you do not expect that independence to be always true. More often than not, the contributions of the two species to the surface pressure and surface potential is not simply additive. What do we interpret it then as? The same way, if monolayer properties are different, monolayer probably is a compound. It is not a simple mixture of two species which would give additive properties, but here there must be something more to that, and that is what we imply by formation of a molecular complex. The two species in the monolayer interact in a much stronger way, producing a behavior which now is not a linear combination of the contributions to the surface pressure and surface potential. So, these molecular complexes and their formation is something that we would like to study in more detail in the next lecture. I will just prime that discussion by citing a few details here. Such complex formation, which would be function of the polarity of the head groups, lengths of the hydrocarbon tails, and shapes of the hydrocarbon tails, these would all come into picture. An example is when you inject dilute solutions of substances of the general structure CH3 CH2 11 times X under monolayers of say cholesterol or proteins at air water surface, the reactivity is found to follow the following order. If X is NH3 plus is most reactive, more reactive than sulfate, more reactive than SO3 minus, COO minus, and lastly NCH3 3 plus. So, complex formation could be actually studied on similar lines as we understand chemical reactions in terms of order in the reactivities of the group which matters X over here. So, we will stop here for today and resume the discussion further on surface reactions in next lecture.